Yeah, so yesterday we looked at monoids, which you remember at least from last year. So we said it's a semi-group, so it's a binary operation, which is associative. The difference with Haskell being that we can now actually enforce these constraints. And then to make it a monoid, we throw in a neutral element, which is, as its name suggests, neutral with respect to the binary operation. And then we saw some examples like lists and endo functions. And then we saw that fold R, which you're hopefully familiar with, can be massaged so that we're starting to slowly make TROT appear. That is to say, given such a function, we're turning a list into an endo function. And then we said, well, we can do better than that. We can, for an arbitrary monoid over A, use a function from X into A to turn a list of X into a single A by just crushing the content of the list.
Yeah. And there's something fundamental about this, which is that, I mean, if you can think of building a tree of operations that are the semi-group operation, the diamond, and you occasionally have dotted about the place some neutral elements, and then other than that, at the leaves of the tree, you've got some actual values. What we're saying is it's only the list of those values that matters, not the branching structure of the tree. The branching structure of the tree is neither here nor there. So we're saying to some extent that you know, monoids are fundamentally about combining lists of stuff which might be empty and might have two or more things in them.
Right, so we got this definition and then we proved that it is a monoid homomorphism. So what is this saying? Well, this is saying that basically we are preserving structures, we're transforming things while preserving structures. And how do we see that? Well, we're mapping the neutral element for lists, for the list monoid equipped with append, to the neutral element in the target monoid. And then we're mapping the binary operation in the list monoid with append to the binary operation in the target monoid. So these things are transparent. And then we said, yeah, okay, this is the motivating example, right?
Yeah.
Saying that we can recover fold R as just the fold map over the endofunctor monoid.
Yeah, let me show you my favorite example where you do something like this. I'm just going to label these things with 1, 2, and 3. Well, I've got a kind of pink chalk here. We're going to do the adding up monoid with the pink numbers. So the neutral element for adding is 0, and then 1 plus 0 is 1, 2 plus 3 is 5, 1 plus 5 is 6. Okay, now what happens is that there's an operation, let's do 2 to the power, is not just an operation from numbers to numbers, it's an operation from adding to multiplying. So let's see what happens if we do 2 to the power to all the data. Right? So 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. 2 to the 1 is 2. 2 to the 5 is 32. 2 to the 6 is 64. And what you'll notice is that if we look at the pink numbers at each node here, we get a true fact about adding up. 1 plus 0 is 1, 2 plus 3 is 5, 1 plus 5 is 6. When we do the operation 2 to the power on the data, we turn the same picture into a story that tells true facts about multiplication. Sorry, I should have put a 1 there for the neutral element of multiplication. 2 times 1 is 2. 4 times 8 is 32. 2 times 32 is 64. So that's the point, is that this thing is not just a function from numbers to numbers. It's a homomorphism which maps the additive structure of numbers to the multiplicative structure of numbers, and it preserves the truth in the whole picture, not just acting on the data. Good job we found the colored chalk last week.
Right, so one thing I wanted to do, which is a bit of a well, is it a departure? Not really, I guess, is to do the ACK-based version, the accumulator-based version of FoldMap, because that's an instance of generalizing the induction hypothesis, which we've seen in the coursework, which is an important technique to understand. And it's also, the correctness of this thing relies on the fact that we can basically reorder the operations as long as we're keeping the left to right. We can rebracket the operations as long as we're keeping the left to right ordering of the arguments. So I'll put it in the same module, because I'm relying on the existence of the same thing, except that now I'm doing something like this. So I have my function, I have my lists, and I have my accumulator. And then I want to inspect my lists. And if I have the empty list, I'm going to return the accumulator because I've gotten all of my values. And then if I have a non-empty list, what I want to do is fold map ACK. I need to get this right. And I can see how it's going to go in my head. The computation, I'm going to put the computation on the right.
Yes.
I think that's
that's correct. And that's one reason why, unless you're actually going to use higher order endo A, I would put the accumulator to the left of the list.
Right, yeah.
Just so that you can see spatially what's
see.
going on. The idea is that you're working left to right, and ACK is the story so far, and then the rest of the list is the stuff to the right of you that you still haven't visited yet.
Yeah, because if we had put f of x to the left, you can see that then if we get y at the top of the tail of the list, we'll get f of y, f of x. So we've exactly reversed the order of the operations, which is what we shouldn't be doing.
Yeah.
So, but if we move this around, it's true that it's a bit more.
So yeah, that's a piece of free advice for someone who's been making mistakes writing computer programs for the last 47 years is that you should arrange your data and the order of your inputs and so on in order not to do any janky spatial transformations in your head to figure out what things should look like left or right. Keep that as simple as possible. Introduce a type of backwards lists if that's what you need, so that it's sort of spatially sensible. And here we're not doing any swapping now.
Yeah. So you can see the alignment is just all over the place, but just to show you that we're respecting x's in the left to right order. And now if you want to prove that these two, okay, then I need to kickstart it, I suppose, with, I used to have it in my keyring, but I don't anymore. Up. And we'll start with the computation with a f. Well, I suppose we don't need to introduce x's anymore. F. And of course, we start with the neutral element because that's the thing that will be absorbed as soon as we start crunch, and so it won't have any impact on the overall results. And so then if we want to prove that this is equivalent to the previous one, so why would we want to do this? Well, you can see that here, well, maybe let's go back to the other one. Here, what we do is that we perform a subcomputation, and then eventually we get the result back, and we combine it with the result of calling f on x using the diamond thing, which means that if you're thinking about the execution of this, you're going to push stack frame corresponding to like the work that you still have to do once you come back from the recursive call. And then, well, you're going to grow your stack, and it might blow up eventually if you have a huge list that you're traversing. For this one, on the other hand, what we do is that we call ourselves recursively after having modified the accumulator, meaning that we can compute this first and then just do a simple recursive call with no need to store a stack frame because we'll return the value immediately to the caller.
Yeah. It's a tail call. So
Yes.
this is readily transformable just into a flat loop.
So yeah, so this is why we often have like accumulator-based solutions in functional programming. And to prove them correct, the recipe is more or less always the same. So the problem is that if we do this, fold map prime correct, for x and set and f x a. Okay, I didn't need the, well, maybe I can do it this way.
Yes.
Fold map fx's equals fold map prime fx's.
Classic.
Maybe the other way around.
Yeah. Right. Your everyday lesson in methods of Alan Bundy. Alan Bundy was now retired, the professor of artificial intelligence in the old sense of artificial intelligence at the University of Edinburgh. Spent a lot of time on automating theorem proving. You know, I spent a great deal of time teaching first years to use methods that Alan Bundy's computer programs have mastered. And it's terribly funny because they try and use AI 2.0 to cheat on homeworks, which are assessing skills that AI 1.0 was really good at. I mean, anyway, yes.
Yeah, so I mean, fold map and fold map ag, they're defined by induction on the list, so you might as well just split the list and have a look. And if you start looking at this, you might get the wrong idea because when the list is empty, you kick-started the computation with neutral. Here, with the accumulator, is just being returned. So you get neutral equals neutral. Yeah, I know how to prove this.
It's looking good. It's
Pretty
looking good,
easy.
isn't it?
And then we have this case. Okay, maybe I can do a bit of computation. So now we're getting stuck, basically.
Yeah.
Because
Because
I mean, I can rewrite sem of like fold map prime correct fx's because I have a fold map fx's here and I have one here. So I can attempt this. You can see that now we have like new showing up here, but here it's not new anymore.
right.
And that's to be expected. I mean, the whole point of the accumulator is to accumulate values. So it's not going to stick to just being the neutral element. It's going to keep crushing, like assimilates all of these intermediate values we're computing. So the trick is to just not do that.
Yes. So in particular, having introduced the accumulator, you're going to need to prove something which says something sensible about any accumulator, because that accumulator is what's changing from step to step. So you have to be ready for that change. Yeah, so what's happening is that Guillaume is introducing an extra variable in the statement of the proof, which is not the variable we're doing induction on. So the variable we're doing induction on has to get smaller as we take inductive steps. But the other variables in the problem, we can instantiate however we like, differently in the recursive calls. They're allowed to change, and that introduces some flexibility in the proof strategy. So Alan Bundy would call that variable a think variable because we want to use it to absorb the differences between what's happening in the induction conclusion and what's in the induction step. And here, that's exactly the accumulator changing. So yes,
What are we going to say?
Are we going to say this?
No, we're not. The accumulator is affecting the output on the left of the equal sign.
Yeah.
So the accumulator better be showing up on the right-hand side of the equal sign. And what's more, we know we needed to have some spatial relationship with the x's. The accumulator is to the left of the x's, and it's the story so far. And what we're really talking about is how to add up all the things with two different strategies, given that we've got as far as the accumulator to the left of the x's, and we're just changing our strategy for traversing the rest of the x's. So you are going to want to put accumulator diamond there. And then when you kick that off with the neutral element, monoid laws say no problem.
Yeah, so let's do that actually immediately. So I'm going to open my...
You need your accumulator in there. You got to off by 1. Okay, you're going to...
Yeah, I'm going straight to the...
Yeah. Checking fitness for purpose.
Which, I mean, both approaches can be bad in their own ways, right? You're assuming you're going to be able to come up with a proof of this intermediate lemma and just like push on with the rest. And then after 20,000 lines of proofs, you come back to this thing and you actually notice that it's not provable. It's actually untrue.
It did the trick. Pity it's false.
It was just a bit too strong of an assumption. Conversely, you can spend a lot of time proving this and then realize that it's not actually strong enough to get your conclusion. So, I mean, here I know it's going to work, so I'm happy to just do it. So, okay, or maybe I can do it the long way. Okay, so I'm going to use this correctness here. A bit of solving, no? With my f. Okay, x's, no.
No, neutral.
Neutral. Oh yeah, the spatial thing. Okay.
Yeah.
All right. And you can see here that we have something which is exactly the new diamond constraints. I mean, this is part of the...
Oh, you left that implicit.
Oh yeah, of course. Okay. Right, yeah. So part of the design decision yesterday was to leave the x implicit because it's exactly on the right-hand side of the equality. So the unifier will always be able to grab it from the right-hand side.
Yeah, so that's the
so
thing.
I don't know why.
If you haven't clocked the rules of this game yet, right?
Yep.
Using these color schemes, green stuff is the enemy. We call it green slime. But if you've got purple stuff, that's variables that are sitting underneath blue stuff or red stuff, then because those things are equal only to themselves, they'll be able to solve the equations for the purple stuff. So here we see, and pink won't do either. Pink is basically morally green. So as any member of the Green Party of England and Wales will tell you. So in the equation that we had for associativity, there was no way we were going to figure out x, y, and z. But in the other one, in the neutral absorption ones, there was an x directly under the blue equality sign, so we're good.
Okay, so if we manage to prove this, then we're done. And hopefully we're going to be able to prove it. So once again, we're playing the why is it stuck game. And here, fold map ACK is defined by induction over x's. And fold map is also defined by induction over x's. So we're just going to look at x's. In the base case, we, on the left, return the accumulator because it's been threaded through all the way to us, and now we're reaching the empty list. And on the right-hand side, well, the fold map returns the neutral element, but we've generalized the statement of the lemma to always have the accumulator on the left. So we are left with something that's just the symmetric of, oh no, why is it slow again? No, the battery is fine. Okay, of the diamond new no argument proof.
Cool.
All right. And then in this instance, we just take it slow, right? We have a fold map on a smaller list on the left, so let's just start with
So
this.
yeah, induction hypothesis goes straight away with the tail call.
Yeah. So there's going to be probably more than one step. Oh. Well, let's do. Oh no, there is
Yeah.
computation here. It's not reduced enough. Yee. So just for the sake of documentation, we had a non-empty list, so we computed f of x and shoved it on the right of the accumulator. Now we can use the fact that fold map app is correct. And here we have the modified accumulator, which we can do now that it's universally quantified in the statement of the theorem. And we have our x's, and that gives us this thing, which, okay, a bit of computation on the right also would be useful. Yes. And now we can see that we are almost there. The only thing that's in the way is that the parents are not grouped the same way. So the whole point of like having a monoid, well, a semigroup, is that we can just move the brackets around however we want. So I can just look at it. So it goes from left to right, and oh, it's in the right direction. Perfect. So here we need to specify what the values are. The last one might be inferable from the first few ones, and we're just moving the brackets around.
Yeah, and it's just one of those reassuring things to do a roll call. You see, I don't have an umbrella, and I'm not going to jump. But you can see diamond neutral up there, neutral diamond down here, associativity in the middle, all present and correct. You needed the whole of the monoid structure to explain why essentially doing a left nested computation gives the same answer as doing a right nested computation.
Okay. So that's pretty good.
That's cool.
Move this over here. All right. So then I thought we should define what it means to have a homomorphism between monoids.
Yeah.
Do you want to do it, or?
I can try. So I want to give myself a couple of monoids now. So I might want to say module.
Yeah, so we've said informally what it meant to have a structure preserving map between two monoids. But of course, we may want to actually say formally what it means, because this way we can just assume we have a generic one and implement generic operations over like any monoid morphism we may have.
I might, yeah. I'm going to call this SC and TC for source carrier and target carrier, so that I can have a monoid S on the source carrier and a monoid T on the target carrier. Where? Okay, and now I'm going to say, what on earth does this consist of? Well, any minute now. First of all,
you need a name for your module.
I do, and I'm going to call it underscore. Right, now I say module S equals monoid S, module T equals monoid T. Module names are not variables, so this is suggestive punning rather than an actual clash. Okay, so I've got the useful equipment here. let me see if I've got this right. I'm now going to define a record, which is going to look strange because it's infix when I define it. But once we're outside this module, it will have a source and target either side of it. So this is probably not the name you wanted, but
Sure. How do you pronounce it?
Monoid arrow.
Okay.
Right. So right. So what we're going to say? Oh, I've got to say what it is.
Oh yeah.
It's say hom fun goes from SC to TC. So you got to know what to do to the data, and then you got to say it preserves the truth of all the pictures. So I'm going to say that hom fun of S dot neutral is T dot neutral, and then I'm going to reload the file because I'm afraid of messing it up. And then I'm going to choose a terrible name, which says for all S0, S1, if we do hom fun of S0, S dot diamond S1, that's equal to hom fun S0, T dot diamond hom fun S1. Is that what you wanted? So it doesn't matter whether you do the pink calculation and then turn the result purple, or whether you do turn the pink inputs purple and then do the purple calculation.
Okay. Examples. Well, we have a bunch of monoids lying around, right? What do we have? We have list, we have endo. And that's it. Do we want more? Maybe we want more.
Do we want more?
Well, let's start with these ones. So let's give an example. Let's see. So if we have we've seen one, right? We've seen fold map, but fold map was taking a function. Or we can define crush, I suppose. Let's define crush. So let's say that we're in a context where we have a set and a monoid over that set. And then I'm actually going to open it. Monoid M.
A monoid.
And then I want to define crush as being the thing that takes a list of x's and just produces an x. And how do we do that? Use full map over the identity. So I didn't even need to open it. So that's a bit silly.
Yes, hilarious. Well, you know, by writing full map, we did write all the monoid homomorphisms from lists.
Yeah.
Not, although that's an interesting thing because we, so far I've only just said that. We should prove that.
Yeah, so I want to say, I'm not sure what to call it for now. But I want to say something like this, right? Or rather M. Yes.
Yeah, why not just call it crush home or something?
So what is this saying? If you remember, the list
Oh yeah, you're going to want
definition was proving that for any sets you can build the monoids by taking list of values in that.
you're going to want to open my record public.
Yep.
Should have done that.
Or maybe I can open it here.
Yeah, but you'll always want it to be public, I think.
Well,
Fine.
maybe we'll have more than one at some point.
We will have more than one, but
Yeah.
somehow you'll always want the co-patterns to work nicely.
All right. And so, as always, when you're defining a record, no, okay, let's roll back. So I said, so list is turning an arbitrary set into a monoid by just taking the free monoid, as it were, but by freely saying, well, you can have any number of x's, and by append, you just have this associative operation. And here we're saying that if x also happens to be a monoid, then we can have a monoid homomorphism between list of values and just a single value in it. And there's no price for guessing what it's going to be. We're just going to crush the entire list by using diamond to combine the values. Okay. And then we need to prove, oh, this is getting nasty, that the neutral element in the list monoid, so the empty list, is getting mapped to the neutral elements in our monoids nu. But with a bit of normalization, this is exactly what fold map was doing, right? Fold map on the empty list was just returning the neutral elements. So that's REFL. Or rather, we had a name for this, right? It was fold map nu.
What did we call
Fold
it?
map empty, I think,
Yeah.
ID. Or MID? Yeah.
Yeah.
The fold map empty was saying if you have a monoid in scope and you have your function, so in our instance it's just the identity, then it reduces. That was just the way it was defined actually. For the fold map plus plus, there was a bit more information lying around, because we needed to do like some proof steps via associativity. And this will come in handy now that we need to prove that we're mapping diamond to diamond. In the list monoid, diamond is append, and in our local monoid, well, just diamond, it's left unspecified, right? Because it's an arbitrary one. Okay, so that looks exactly like this, where we have our monoid, we have the identity function, and then these are implicit in your definition. Ooh. Maybe they should be explicit.
Yeah, they probably should, because they're under green things on one side and pink things on the other. So they're unlikely to be all that guessable.
Yeah, I mean, if you think about the list monoid, right, this is going to be append, and there are a linear number of ways to split a given list into a prefix, append, suffix. So there's no hope for it to be just automatically reconstructed. Okay.
Cool.
Ooh. Good day comments for squishing. So that's the next thing. Okay, so the idea now is that this is, as Connor was saying, some kind of fundamental action on monoids, right? Because whenever you have one, you can just crush the values.
And it's a thing to think about is that there's an alternative entry point to what it is to be a monoid at all, is to say that whenever you have some list of things possibly empty, you can bung them all together. I mean, you ought to be able to reconstruct the neutral element by crushing the empty list. And you ought to be able to reconstruct the diamond operation by crushing a list of length 2. So, crush is generated from neutral, and diamond, but you can go the other way as well. And it becomes interesting to ask, what should the laws of monoids be if you're just saying monoid is something with a crush?
Mm. Um,
Because the answer to that question is quite a revelation, but it's also quite sophisticated. So I'm going to leave that hanging.
I think here what I wanted to do is, so whenever you have a monoid morphism, if you have a list of values in your source monoid, you could either crush the list and then transport the value across using the monoid morphism, or you could transport all of the values individually and then crush the resulting list. And if monoid morphisms are well defined, they should be the same thing, right? Because as we've said, I mean, this is what makes it work basically, right? No matter what you do in the empty list case, it's got to be the same.
Yeah, so that's true. And what's more, it's the same story, right? You know, if you imagined that monoids were just introduced by saying, okay, there's this crush thing, then how would you define a monoid homomorphism? You would have to say, well, there's this function on the underlying types, and it doesn't matter if you do it to all the things in the list and then crush afterwards, or if you crush the list first and do the function once afterwards. You know, that's what you would say to introduce that idea if we'd taken the crush version of the monoid story. So it's important to show that that definition would also have worked, right? That it's a consequence of this one.
Yes, so it's going to be a bit wordy, but I want to say something like this.
Do we have map already?
We can import it. And then we have S to T. So that's the S monoid arrow to T function, okay? And what we want to say is, I mean, crush.
You might, okay, you might want to open
map, something like this.
Yeah.
What we want to say is that if you have a bunch of source values,
you will want that to be explicit.
Yes.
Pretty sure.
Then if you crush them, and you right, that's what I want to open. Yes. If you apply the home fun on the result of crushing everything, it should be the same as crushing something. Or crush is taking all of these arguments explicitly.
Did I? Yes, that's...
Yes.
Okay.
All right. So if you're crushing at S on your inputs, I should maybe make these, give them an explicit type.
List SC.
Right. Right. Yeah. It's the same as crushing ST, where you've point-wise modified the inputs. And point-wise modification for lists, it's going to be
map.
So you should know map, right? I'm just applying the function everywhere. So there's going to be list map of the home fun on S's. And I need to list. Well, I can just import it. There are no clashes, right? All right. Okay. And I mean, it's not too complicated, right? We can just perform induction on our S's. We have an empty list. Then we have a bit of normalization. We get to see that the home fun should take the monoid and S, the neutral element of the monoid and S to the neutral element of the monoid C, but that's exactly what the Nunu rules were saying. Okay. And in this other instance, what do we have? Well, we have the home fun. Oh. These new lengths are really annoying. We have the home fun taking S diamond together with the recursive call to diamond of home fun S and the other right hand side. So again, taking it slow, we can do a bit of reasoning. Up, up, up.
Yeah, you would be sensible to repeat the module definitions that I made, just to give yourself S and T.
Okay.
That would be pretty. So just steal those two.
Whoop. Yeah, I don't know if the pretty printer is going to be good enough to actually take advantage of that.
Well, we'll see. Oh, is that?
Oh
yeah, ha 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 ha. Good stuff. And you're going to want to do the same here, actually.
Yeah.
We can fight the module system.
Yeah, whenever you want something not to be polluting the module, you can just make them private and then they will never leak, hopefully.
Yeah.
Um,
Right. So yeah, now you're getting s.diamond, which is nice.
So let me do QED here and a bit of like filling in.
Yeah.
I don't like this, but
Yeah, you want ID for that.
oh no, that was crush, right?
Yeah.
I don't know what. Yeah. I think Pierre Buty had a good heuristic not to unfold these. Right?
Yeah.
Oh no, but because we're defining in terms of format and we wanted to reduce over the cons, it's going to be unfolded anyways. So
Yeah.
it would need to be really clever to be refolded. All right, so here we have an omfun on the outsides and a diamond on the insides. This is exactly what diamond is telling us. Should be fine. Whenever you have a diamond on the inside, you can push it out and the home fun will just fall through on both sides of the thing. So we can use that one step and a bit of constraint solving. Yes, this is good. Oh, and we're basically there. So I'm going to start from the end. It will be easier, I think. But I have this thing that I don't want to touch on the left-hand side. And here I have an occurrence of the result I'm trying to prove at a smaller list. So I can just use, oh, okay. Otto was a bit too eager to use any lemma in scope. Okay. And now we can see we've actually bridged the gap already. So I can even remove the extra step that I had in between them.
Once again, reassuringly, both properties in evidence.
Yeah. So then basically it's up to you to decide whether the home fun is cheaper and you're willing to do it in parallel to everything and then crush the results, or whether home fun is really expensive. So you start by crushing first and then you perform the home fun. Like,
So for example, adding is a hell of a lot easier than multiplying. So you'd go, oh, 1 + 2 + 3, that's 6, 2 to the 6 is 64, rather than all the other crap.
Yeah. But crucially, you know that it will always give you the same answer. So that's really cool. Okay. And then in the last 5 minutes.
Yeah. Oh, do you want to do that, or do you want to do the all homomorphisms out of lists are given by full map?
Okay, you can do that if you want. Then.
Yeah, does that work? Because category is not a 5-minute job.
Well,
okay, so where the hell are we?
it's just a fancy one.
Yeah.
That's what the comment was saying. So
Yeah. Right. So what have I got? Right. So okay, what happens next is that what do I need? Just trying to figure out how many levels of indentation I'm in. Okay, I want to be further out. Right. So somebody's going to give me a an element type, and they're going to give me a monoid carrier, which I'm going to call TC. That's also a set. Oh, goodness me, XTC. Excellent band from the 1970s. And we've got some T monoid on TC. And then someone is going to give us some H, which is a list X monoid to T. And I'm going to, first of all, open I'm going to open that thing. And I'm wondering if I can prove in fact, I just tweak my so that's implicit.
Right. This is a record type, so these things are just sitting there ready for the unification algorithm to pick them. Ooh.
All right. So I want to say this thing is a fold map, right? That's to say, I'm going to say that for all x's in list of x, the hom fun of each, I can just say hom fun, can't I? Hom fun applied to x's is equal to fold map something of x's. Oh, and I've got to make that infix. So, and annoyingly, of course, this notation is designed for after the module is open. So, of course, I'm leaving some.
Oh, you need a monoid.
Okay, that's my monoid. That's for T. Good. And I'm leaving goal 0 blank to just for dramatic tension. Right. So let's try and prove this without knowing what the function is and see if we get a big hint.
This is a good strategy, actually.
Okay. So here, we have to prove that the hom fun of nil is the monoid neutral. But, you know, let's not faint with amazement. That's just true anyway. Okay. So this might be more of a clue. Let's look for some ingredients here. Is anything happening? Yeah, something is happening. I should take my own advice, actually. How do I? It's doing that thing that drives me nuts. Right. Can we see any better what's going on here? Right. So what do we have? It's slightly better. We're going to do fold map of our mystery function over x's, and that's going to get t-diamonded after whatever we turn x into. And that has to give us the same thing as whatever hom does to x cons x's.
And this is the one case, right? We're writing this
Yes.
instead of this. Is
Yes.
actually a good idea.
Exactly. I want you to jump in because
Oh.
this is worth doing the slow way.
Okay.
And my fingers aren't up to that much Unicode. We are, at least if we're going to finish this in a sensible time, right? Because what we want to do, you can see, we want to take this apart into two tasks involving hom fun for x and hom fun for x's. So we're going to exploit some algebra. We know we're going to want to use diamond from this monoid homomorphism.
Let me say this thing.
You'll need a QED.
Sure. Oh. Okay. I'm hoping that's enough. We'll see. So we're starting from this thing, and as I was saying, we like shout out to you for writing this in 260 and in 316. But here it's actually the right thing to do because this is the diamond for lists, right? And we know that H is a list homomorphism from list of x to t, meaning that if we have a diamond inside, we can pull it to the outside and the home fun will fall through. So this is equivalent by diamond. Okay.
You have to say diamond with.
Of the singleton lists and x's to home fun on the singleton lists. It's a shame. Oh, we do have notation for it actually.
Yeah.
List base. Oh, no.
Cool.
It's usually terrible to use, but in this one instance, it's going to be fine.
Yes.
Never imported. It was a mistake to add it to the library.
I mean, stealing unvarnished, unadulterated square brackets, not to allow that notation to be used for anything else ever. Such a mistake, you know.
And
massive opportunity cost.
It's a definition, right?
Right.
It's not a constructor, so it's not disambiguated by. There's no type-directed disambiguation, meaning that you cannot have multiple of these in scope. They will clash. So it was a horrible decision. But
anyway, we've
right.
just spotted that doing hom fun to singleton x is a way of turning one x into the carrier of our monoid. So could that possibly be what goal 0 has to do?
Maybe. Do we want to do it yet already?
Yeah.
So let's do it like this. Some fun. Poop.
Yep.
So if we have a crusher and we have a single value, well, you can crush the singleton list.
I think we are going to win.
I think we're going to need more steps. Maybe 2?
No. Isn't it a job for...
I hate this. Okay. So here we're going to have the recursive call, right? So we have this.
Yes, that thing.
Took, and then underscore is fold map underscore x's. Oh, could not parse.
You need to do some Kong business.
Oh yeah. Okay, my bad. I was doing a cubicle move. You called it something else. Oh, dashes.
Yes.
Okay.
Yeah. Okay.
Oh, are we already there?
I think we are.
Oh yeah. Well, this one looks slightly nicer, so I'll pick this one. Oh yeah. Oh yeah, no, because I was thinking this introduces an extra neutral, right?
Yeah.
But it doesn't matter for this specific proof.
Yep. So that's the way of saying that fold map is all the monoid homomorphisms out of list.
Which is pretty crazy to do.
Yeah.
Because we don't have access to the codes of the functions or anything, right? It's just a purely external statement. Very nice.